So we've got two topics for today's class. We're going to start today with a unit on building our own list-style data structure. So the idea here is now, we spent Lab 1, A and B, working with the built-in list. But now for Lab 2, what we're going to do is make our own version of list that follows a certain set of rules that we lay out for it. So this week and next week, and then week 8, which is the first week in November, is going to be a whole bunch, a series on how to make classes that support this kind of model. So today we're learning about self-referential classes, and then next week we're going to be learning about list classes, and then there's going to be a couple of other parts that we're going to plug into our list classes, like enumerators, for example. So there's 3 weeks there worth of content that will help us build out our custom list. So starting today with social classes. The self-referential class is a class that refers to another instance of itself. So basically, a self-referential class is any class that has a field or a member variable that is of that same class type. So it's similar to like a recursive database relationship. If you think back to when we learned about one-to-many recursive relationships in your SQL class way back in the day. And it basically was a relationship that points back around to yourself. So why would a class need to contain or refer to other instances of the same class? Well, when you have one object that is related to other objects of the same type. So here's a real-world example using people. If you have a class to represent a person, and that person has children, those children are also other instances of person class. So if you imagined writing a class called person, and we wanted to keep track of that particular person's children, that one person would have a list of associated other person objects. So our class definition might be something like this, where inside our person class, let me just get a pen here, the class is person, and then we have a list of other person objects. So whenever you have a class that has a reference to itself, either one reference, or in this case it's a list of other references to the same type, we call that a recursive or a self-referential. And we can use a class like that to create a tree structure. So if we look at someone's family tree here, if we start with Alice, I'm going to go back a bit just so that we can say we have a name and we have a birthday and then we have a list of children. So for each person object, the person has a name and a birthday and the list of children. Now in this case, Alice has a list of 3 children, but each one of those children is also a person object. So every person object has a name and a birth date and a list of children. Now the list might be empty. In this case, see, there's no list associated with this person called Jennifer. It would still exist. It would just be a list of person objects with no objects in the list. So it's an empty list, or a list with a count equal to 0. So whenever we have a self-referential type of class, we can use it to build relationships. Now in this case, when we have one class containing many references to other objects, that builds something like a tree, where one person has a list of many other persons. And then each of those persons might have a list of many other persons, and so on and so forth. We might also have a situation where it just contains one reference. So instead of having a list of that data type, if your class has just one single other reference, then we would end up with a structure that looks like this. If each person could only reference one other person, then we end up with this linear kind of chain. So when your class contains a list of those objects, then you end up with a tree. And if your class contains only one of those objects, then you end up with a linear list object. Another familiar example of self-referential classes, forms contained inside of other forms. So on your Lab 1B, you're turning your game into an MDI application. And what an MDI application does is the first form that opens, being the parent. Let me draw a form here. When we have the parent form, and then the parent might open several child forms. So we have a situation where a form has a list of child forms inside of it. So we had the form that was the MDI parent. And if we set these child forms to all have the same parent, it's a form referencing another form. Another example is the folder structure in a Windows file system. Each folder can contain files, but it also can contain other folders. So if we were to make a class called folder, it might have a list of other folders. Inside it, and that's a self-referential situation as well, where one folder can contain other folders. Now that's not all it contains other things, but as long as you have that repeated class name, like we had in our person class. So all of those ones would create a tree structure. But we're going to stick with the more linear structure to start out. We're going to come back to trees sometime like late November, early December. For now, we're just going to stick with linear structures. So in a linear structure, we have a situation like in this diagram where each item has just one element following it. So if item A is the first one, and we follow like a straight chain, so it doesn't branch off at all. We can't go any other directions or anything like that. It's just a straight linear chain where you go from A to B to C to D. Now, if we wanted to represent something like that in code using self-referential classes, then we would make an item class, and each item class would need to contain a reference to another item. So in order to provide the link to the next item in the list, our item class contains a reference to the next item. So if we were to make something like that, we make a class. I think I'm getting pretty good at writing with my mouse. We make a class called item, and because there's only one item that can come next, we would define it like that. So for every current item, there's always one more item coming next. The last item in the list would also have this next variable, but it would point to null, and that's how you know that you're at the end of the list. So if we look back at our picture for a minute, if we have we create an item called A, and we want to define that B comes next in the list, we would say that A.next equals B. and b.next equals c, and c.next equals d, and d.next would point to null. We usually don't show nulls in our picture, but we have to consider the fact that, of course, the null is still there, because if it's an item, it's always going to have an item called next. So I'm going to start a project here in Visual Studio so we can get some actual code to give us an example of this. Let me just create a new project for us. Boy, my computer's going slow today. Okay, so here's our console application. Just gotta find a good place to save it. Okay, I just called it self-ref. I know that's really tiny on your screen probably. So while this thing is being created, usually we do this as an in-class exercise, but since we're not in class, I'm going to step through this demonstration. So I'm going to create a self-referential class representing an item. We can give it a few identifying properties. So keep in mind, it's just like any other object class. So if you're creating an object representing, a pet, you might have things like the pet name, the pet birth date, the pet species, the fur color, all the different properties that go along with the object that you're creating. But then you have that one extra property that points to the next one. We want to make sure those properties have public access for now so that we can use our console window to test it out. And then in the main program, we're going to create a few new items and link them together to make a linear structure. So this is going to be the beginning of creating our linked list. So here's our main project. I'm going to create a new file for the item class. It's called it item.cs. Okay, so let's see here. What do items have? Well, the items that I wrote, if we look at the picture, looks like each item has an associated letter, A, B, C, or D, and it looks like also each item has an associated background color, red, pink, light purple, and dark purple. So I'm going to add those two things as properties of an item, along with our next pointer, so that we can connect the items together. Let's see here. So I'm going to say, let's do char. I'm just being lazy and making these things public. What you should be doing is good class design that we learned in previous classes, where you make these things private and then provide accessors and properties to control how they're, all that stuff that I taught you before. I'm just not following it because I don't want this demonstration to take forever for me to build the class. You guys know those rules by now. You're expected to follow them when you do your labs and tests. So we have these two properties of item, letter, and back color. And then we have our self-reference that we call next. Now we're going to make the constructor. Now I'm going to leave out the next pointer in the constructor for this particular demonstration because we're making a typical linear linked list. And most of the time when you create the new item, you haven't yet inserted it into the list. So therefore, it doesn't make sense to create the item after this one when we're still in the middle of just creating this one. You know, we can't create item C and say already that it points to D when D doesn't exist yet. So we're going to have to set up the items first and then set up the connections after the fact. And that pretty much tracks with how we use other list classes as well. Like you create the new item, and then after the new item is created, then you add it to the existing list. So we want to make sure that we separate those two steps. Otherwise, we're going to have some issues trying to create it. Okay, so we're going to say this and this. And we start with next as null. So when you're creating a new item, it doesn't yet exist in the list, so therefore nothing comes after it yet. So here's my item class that refers to another item. Okay, I'm going to take this and I want to try to put them side by side. Here we go. Don't need the toolbox right now. And we'll squish that out of the way too. So we can hopefully, see how these two things work. Okay, so now in our main method, I'm going to create our first item, and I'll just call it A. So the first item in our list, item A, that was the red one. And then we have the second item in our list, which was item B. Item B is a pink one. If we want to point them to each other, the way that we do that is I'm going to say A.next equals B. Now, in order to test it out, I'm going to create a toString method in item so that I can, quickly access and view those values. Instead of it just saying selfref.item, I'm going to return a string that represents the item. Let's just call it, oops. So we'll show the letter and the color. Got my semicolon. Here we go. So I'm going to use my console window. To write out my A object. And then I'm going to use console.writeLine again to show me what A.next is. That's obviously going to show us the B object. We can watch how A and B get connected together. I'm just enlarging the font here. There we go. So there's our A object, and there's A.next. So notice that if we want to actually go through the list, I don't need a reference to B. All I need to know is A. Let's add some more items onto our list. Now we've got C and D. Now, if I want to add C and D to the list, I've got two choices. I can use the existing references that I have and say, okay, well, after B, I want C. So I'm going to say B.next equals C and C.next equals D. That will connect them all together. That's one way. The other way is I can say A.next equals C. So you follow along, A.next is B. So we evaluate this to B, and then B.next becomes C. So A.next is B, B.next is C, C.next is D. So we can build a reference traversing just starting from A. We don't need references to all of these B, C, and D. Let's continue on with writing these all out. Now hopefully you can see a loop coming our way, because this isn't sustainable if we have 500 elements in our list. Can you imagine 499 nexts later? But it's a starting point, right? We're getting the idea of how we can traverse a single list if we just know the starting point, and we can follow along the .next pointers from one to the next to the next to the next. So all we need to know is where's the starting point. Now I can make this even more efficient where I'm not storing any of these items in a separate location. If I take this and substitute it here, and I'm going to take this and put it there, and I'm going to take that and put it there. Now we don't need these. So the only reference I have now to work with is from A. I don't have local references to B or C or D. But that's okay, because this will still all work the exact same way. I'll still be able to traverse through those 4 elements by following along the .next pointers. Still works great. Now, ideally, what we want to be able to do is traverse a list if we know the starting point by creating a loop. So we can do this with a for loop or with a while loop. But if I create something like this, first I'm going to start at a starting point. Usually when I make loops like this, I call it current, because we're talking about which current item we're looking at. So we're going to start off by currently looking at item A. And then we say while current is not null. So on my first trip through this loop, current is going to be A. So I'm going to say, show me the current element. And then to increment, I want to move to B. So I'm going to say that current is now B. Well, how do I get to B? B was A.next. I'm going to take my current element A, go to the next one that's B, and say that B is now current. When my loop starts again, is B null? Well, it's not. So I'm going to write out the B text, and then I'm going to evaluate B.next, which is C. So current is now going to be C. We start over. Is C null? We write the C value. C.next is D, so now current is D, and we can move through the list that way. So we don't need all these, multiplying .next. All we have to do is move ahead one each time. Still get the same output. So current started out as A and then moved along, going to the next one each time. So we're able to make a really simple linear linked list structure just by creating that self-referential class and then using these pointers. And we could do something similar when we are assigning it all as well. We can move to the next one and then assign a new item. Typically, if we're reading items from somewhere, like the user input, or reading it from a database table, or reading it from a text file, you would move to next and then assign it to some new item that you read from somewhere. So we can use loops to simplify moving your way through the next pointers. So we can move forward through the list, but what about moving backward? If we want to be able to move two ways, then we need two pointers or two self-references. We can add another one called previous that will go along with next. So if we make a structure like that, we call it a doubly linked list. So I'm going to go back again. This one is a typical, singly linked list. I'm just going to get rid of the existing ink here, that we have pointers that go to the right. Now what we're going to make is something that have pointers that go back as well. Because if we look at the code that we just wrote for this, we can go forward, but we don't have any way of going backward. So we can get from A to B, but if we're at B already, we can't get back to A. If we want to be able to get back and make a doubly linked list, we can put a second self-reference. Typically, we call that one prev for previous. When we make the links, we have to set up both properties. So if we think about what happens when we make A, let me just bring this up again. When we make A, if A is alone, it's the first thing that we make, then it doesn't have any pointers pointing either direction. But as soon as we make B, when we make B, we say that A.next equals B, and we also have to say that B.prev equals A. So whenever we add a new element, we have to set up the pointers going both ways. So here when we said A.next equals the new item, if we want to set up the pointer going the other way, and we don't have a reference to this thing other than saying it's the next one from A, we would need to say something like this: A.next, that means B, .prev equals A. It becomes a lot more convoluted. We can do the same things for C and D. A.next is C. So C.prev equals, to point C back to B. Okay, and we can do the same thing for B as well. Now, typically what we would do instead is create this sort of while loop to keep track of where we are and just say, you know, current.next.prev and go back that way rather than having all of these references. But it's a way of manipulating and traversing your way through the list. So if I write out current now, this is going forward because we're using the next pointer. What I'm going to do is we can, you know, start describing what's behind us as well. So if I say current is this, and I say prev was that, and it will tell us what was behind as well. I'm just going to move this over a little so that we can see it when we print it out. Now, this thing might cause us an error when we try to go previous from A. So I'm going to use an if statement to make sure that doesn't happen. There we go. So we can test it out in both directions. So we can forward. From A, there was no previous, but when we're looking at B, it says the previous was A. When we're looking at C, the previous was B. When we're looking at D, the previous was C. And then when you get past D, you're looking at a null object. So obviously, the null object isn't going to have any pointers to anywhere. This is how we can build a doubly linked list. Now, this is only one half of the equation. Each item is related at most to 2 items, one on either side. So if we make a doubly linked list that has 2 relationships, but you can see it's still a linear, that's a D here, it's still a linear structure. It's not branching off or anything. Now, what about a non-linear structure, like a tree? If we wanted to create a tree, each instance of the item class would need to contain pointers to 0 or more other items. Now, one way to do it is to make your item have a list of the same type of item, like I showed you in that person example. But we're going to do a more specific example of a binary tree. So if we were making an element to represent a node in a binary tree is a tree that can only have 2 branches on any node. Now, some of the nodes will only have 1 branch, so it might end up looking like that. Or some of the nodes might have no branches, but the maximum is 2. And we're going to learn a lot more about binary trees later on in the course and using them for searching and sorting and organizing the data. But if we wanted to make a structure like that with our self-referential class, all we would need are 2 self-references. And we call those things left and right. So in a linear list, we say next, and if we're going back, prev. But in a tree, we go left and right. So each node has 2 options for different ways that you can go. So we're going to write a self-referential class that represents a binary tree elements. Let's give this a try. So an element in a tree is usually referred to as a node. So I'm going to add a class called node. And for our tree, let's give all these things a number. And we'll have two self-references, left and right. We set this thing up the same way, where our left and right point to null, because when we create the new node, we have to create it before we insert it into the tree. And we'll have a toString method. There we go. Actually, I'm going to return this a little bit more nicely. Some brackets and stuff so that it can look more like a tree node. Okay, so there's our toString method that returns value, and I put some parentheses around it. So you can imagine it's drawn inside a little circle. So if we have a node class, how could we build a tree out of that? I'm just going to comment out our item class, and we'll make something for the tree. Now, when we make a tree, the first node in the tree, we call that the root. It's a whole tree theme. So we call it the root. I'm going to have the root node have a value of, I don't know, 5. And then I'm going to make 2 more nodes, one for the left and one for the right. So we'll put, say, 2 on the left, and we'll put 7 on the right. Now, traversing a tree is a little bit more complicated. It was very easy in the linear list because there's only one option, there's only one way to go. But if I try to traverse a tree, I have a choice. Do I move to the left or do I move to the right? Well, you know, typically if I want to see the entire tree, I'll need to do both. But how could we traverse through the tree in both directions at the same time? Well, we can't go at exactly the same time. What we end up needing to do is writing some kind of a recursive loop that, you know, tries to go one way and then also tries to go the other way. We're going to leave that topic for later, you know, when we study trees more. I've got a whole other class set up just about tree traversals. So for now, I'm going to say that root.left, so that's 2 on the left-hand side of 2 is going to be another new node. We'll put 1 down there. And if we go to the left of the 7, and that's going to be where we put the 6. So what I've made here isn't what's on the slide, but I made one that has 5, 2, 7, 1, and 6. So root.left. Over here we went root.right.left. So we can build up a tree by taking different pathways to the right or to the left. So we're going to learn more about trees a little bit later. So we're going to change our focus now back to the linear list. I'll take a quick little break, take like a 10-minute break, and come back at 2:55.